So at the end of the last lecture, I introduced this stochastic process that was used to prove the Hooke formula. So I will call the Hooke formula. So lambda is a partition, and the dimension, I call it the dimension of lambda. It is the dimension of the irreducible representation associated to lambda. So as we saw, it is a number of standard Young tableaux of shape lambda, and this is equal to n factorial over the product over all the boxes of the partition of the Hooke length of the box. Okay, so remember, so I draw my partition in this way. Okay, something like that. And if a box here has coordinates ij, say ij, then the Hooke length is a number of boxes which are on the above right or above left, like counted like that. Okay, so you take the product of these numbers, take the inverse and multiply by n factorial, and this is the number of standard Young tableaux of shape lambda. That means the number of ways that you can put numbers from 1 to n so that they are increasing on along the rows and the columns of the partition. Okay, so and in order to prove this formula, I introduced a probability measure, which was supported by the corners of the partition. So the corners are the boxes that you can erase in order to get a new partition of n-1, okay? And so if C is such a corner, then this probability was just the quotient of the dimension. So it was dimension of lambda minus C over the dimension of lambda. So what we saw last time was if you look at this as parameterizing an irreducible representation of the symmetric group, okay, so f of Sn, and you restrict the representation to Sn minus 1, then there is, okay, this new representation will be reducible in general, and it will be decomposed into a sum of irreducible representations. The irreducible which occur will have multiplicity 1 in the dimension, in the representation of, as representation of Sn minus 1. And they will be indexed by the partition that you can obtain by erasing one of the corners of the original partition. Okay? So this was what I call the branching graph of Sn. And this branching graph coincides with the graph that you obtain by looking at partition and connecting two partitions if they differ just by one box. Okay? So I will call this, so in particular, if you take the sum here over all the corners of the partition, this is equal to 1. So really, this is a probability measure on the set of partitions, on the set of corners of the partition, which is depends only on the partition. Okay? So this probability measure is called the cotransition measure. So I think it was named like that by Kerhoff. Well, here is an interpretation, spectral interpretation. Okay, so maybe I should be more precise here. This is not exactly what I will call the transition measure. The transition measure, the cotransition measure will be the measure obtained by looking at the really the projection on the real line, so on the x-axis of these boxes here. So assuming that these are integers, these numbers that you get here are exactly what I call the content of the boxes. So the content of each box is given by etc. Okay? So you look, instead of parameterizing the corners by saying they are corners, I will just parameterize by the content of the boxes. So you see for each corner there is a content, and two corners cannot have the same content. So this is really a parameterization of the corners. And then what we saw last time is that if I look at the Murphy element, so the sum of all transpositions in Sn which are not in Sn-1. So this, if I look at the eigenvalues of Jn in the irreducible representation, so if I look at the image of Jn in the irreducible representation corresponding to this partition lambda, then the eigenvalues of Jn are the contents of the corners. So there is one eigenspace. If I know that Jn commutes with Sn-1, so certainly it is on each irreducible representation of on each irreducible component corresponding to Sn-1, Jn will be given by some scalar factor. And so the scalar factor, as we saw last time, are just the contents of the corners of the partition. So really, if you want, if you write down a matrix, a typical matrix, and you of this representation corresponding to lambda, so you can decompose it according to the group Sn-1. You will have some block matrices like that with zeros outside, okay? And in each of these, you will get some irreducible representation of Sn-1, and two different blocks will correspond to different irreducible representation, non-isomorphic irreducible representation, because the multiplicities are always 1. And the Jn, it will be, since it commutes with Sn-1, it will be given by some eigenvalues, say x1, x2, x3, x4, and so on. Okay? So it will be given by a multiplier of the identity. And the numbers that you get are exactly the numbers that you get here. So the contents of the boxes that you have erased. Okay? And now, this probability measure, what does it represent? It represents the distribution of Jn, if you think of Jn as a random variable. Okay? So remember, I have this space, say V, which is the space of the representation lambda. On V, I have the trace, the normalized trace, okay? And as I said, if you have, if you are in such a situation, you have a vector space V, and you have the normalized trace on the vector space. Then any self-adjoint operator gives rise to a probability measure on the real line by, say, the moments of the probability measure associated with this operator are just the traces of the powers of this operator. So here, this is a co-transition measure. Okay. So we have so last time I introduced this probability measure. We saw that it was given by the output of some Markov chain, the final state of the distribution of the final state of some Markov chain. But here we have a quite different interpretation, which uses these operators, Jn. Okay, And this will be very important for us. Okay, so in particular, you see when you take the trace of some element, of the action of some element of the symmetric group, this corresponds to taking the character, evaluating the character of the representation. Okay, so these values certainly can be evaluated, can be seen as linear combination of character values of the symmetric group. Okay, because Gn to some power is just a sum of some permutations. Okay. It will be a character of the characters associated with lambda.
Just the one of lambda.
Yes, because I have assumed V is associated with lambda here. Okay, but if you take any other representation, of course, if you take any representation of the symmetry group and look at this formula, you can. I mean, in general, you would have more characters than if the representation is not irreducible. It's just. Yeah. Yes, I could do that also. Yeah, yes, it means something. It's just you would just yes, the GN commute, so you can look at their joint eigenspaces, and you get a joint probability distribution on the eigenvalues.
It's not
well, then you would have to. Okay, then you would have, if you want to express the joint moments, say, you would have to compute the trace of, say, Jn, Kn, Jn minus 1, Kn minus 1, etc., J1, K1, and so on. Okay? And this certainly can be expressed in terms of the characters. Okay, you just have a product, you are just evaluating the trace of some sum of permutations. So the joint distribution, we know what is the joint distribution because we have seen that for each sequence of contents corresponding to a tableau, there is exactly one eigenvector. So if we want the joint distribution of all the j's, then we have a probability distribution which has a sum of Dirac measures at the sequences corresponding to Young tableaus, to standard tableaus. Okay. Okay, so we have this co-transition measure, and this co-transition measure will play a very important role in the asymptotic that I'm going to describe now. Okay, but before that, I want to try to give a more explicit formula than this formula. Okay, so this I will introduce another way of parameterizing this diagram, and this other way will be. So I have shown here that you have a local. So if you think of the diagram as, say, something like that, so say a curve which has which is linear by parts, and which has just only slopes of +1 or -1. Then, in order to describe this, you just need to know where are the local maxima and the local minima of the curve. Okay. And okay, so the curve is minus x for x minus x for x near minus infinity. It is x for x large near plus infinity, and then between it oscillates. And so you see that the contents of the corners here are exactly the points where you have the local maxima of the curve. Okay, and okay, and then you can look at the local minima. Like that. So if you know the local maxima and the local minima, you can reconstruct the curve, okay? Because you have all the information that you need. And now it turns out that it is convenient to express these probabilities in terms of these numbers, which are here. Okay, so I will show you the formula. The co-transition measure is a measure which is supported by the local maxima, the xi. Okay? And the probability of xi, what I claim, is that this probability, it's 1 over n times the product product over J divided by the product over K different from I. So this is what I claim, and it's not very difficult to check. I mean, let me draw the diagram again here. So suppose you have some corner here. Okay, so you have some corner here. So as I said Tuesday, if you compare if you use the Hooke formula and you compare the formula for this diagram where you have subtracted the box and this diagram, okay, then you see that all the Hooke lengths coincide except for the length of the hooks corresponding to the co-hooks, I would say, to show all these things which are here, all the boxes which are here. Okay? All the boxes whose hook contains the corners that you want to erase. Okay? Well, now the formula, and now what you have to compare is you have to compare the product of the Hij. So there is a 1 over n, so it just comes from the n factorial in the Hooke formula. That's all. And then you have to compare this to this one. Okay? But then, well, what is easy to see is that if you take the product, if you divide your, so you have to take the product over all these boxes here of these things. But if you are on this here, you see that if you are in so if you look at the first say the first column here, where all the columns which have the same length as the first one, yes, then you see that this product, the products cancel because when you go from this one to this one, you just subtract one, so the products cancel, and in the end, you get this length divided by this length essentially. And this gives you the first term, so that will give you xk. So we suppose that it is x, say xi, yes, xi minus y1 over xi minus x1. Okay, so this is y1 here, this is x1 here, and when you take this product here over all these things, you get this divided by this, which is because you by cancelling the. Okay. And of course, you can continue like that, and you can do it on the other hand, and you get this formula in the end. Okay, so this formula is very simple.
The last two are different.
What?
The last two, when you really reach your peak, are different. That's why you have a different number of factors.
Oh yes. Okay. Yes. You have yes. You have to see that the number of y's. There is one more y than there are x's. Okay. So here there are two more factors, and you see that because in the end you get a 1 that I don't write down, but okay. The one that would be of pain by looking at this. Okay, you just to make the. Okay, there should be 1 times 1 here, but that's for Andrea. Okay. So it's a nice formula. So we will come back to this formula later. So this is what I think all that I wanted to add to my last lecture before we go on. Okay. So well. Okay. So for the moment, I just. But I will come back to these formulas, and later we will see that there is also a transition measure, but we will not use it immediately. We will use it later. So for the moment, I use only this measure. So now I come to the other. So for the first time, I will talk about asymptotics. So, but first I will. Talk about, so as I said at the beginning, there are several scales at which you can look at a large Young diagram. So, and in the first asymptotic, we are going to look at in some sense, shrink the diagram by a factor n. Okay, and this will lead us to. We will see that in this regime, in this asymptotic regime, so we will rely only on very crude properties of permutation to get the asymptotic, really very crude. And after that, when we have understood that, we will make a more refined scaling by scaling the diagram by a factor square root of n. And then we will see that there is some more subtle things which appear and in connections with cards of genus 0 and things like that. Okay, but first let me do the asymptotic. And the asymptotic, when we so we will have a very large Young diagram, and we will shrink it by a factor of n in some sense. So, and this will lead us to representations of S infinity. So first I say a word about representation of S infinity. So S infinity is just the union of the symmetric groups. So we have seen that the symmetric group form an increasing chain of groups, so we can take the inductive limit, and we can identify this, for example, with the set of permutation of the positive integers, which move only a finite number of elements. Okay. So this is an inductive limit. And okay, so representation, so I made some introduction for those who are not familiar with representation theory, about representation of finite groups. So the representation of infinite groups is much more complicated to describe. You need analysis, because then you not only linear algebra, but really you need to make some analysis in order to understand these representations. And for a finite group, I had the theory of characters. And I said that the theory of characters can be reformulated into the theory of positive type functions. So I will recall that. So positive type function. So this is a function phi on a group G is said to be positive type if phi of j I j minus 1. If I take n element in the group, j1, jn, so if this matrix is a positive matrix, so it should be a Hermitian, a positive matrix. Okay, and what I claimed is that usually I will look at normalized positive type functions. That is that I assume that at the identity of the group they are equal to 1. Okay, and what I said is that essentially this positive type function can be viewed as coefficients of unitary representations on the group. So as a function, so it's a function on. You don't say it, but and if such function is just a complex function on the group, and it is said to be positive type if all these matrices are non-negative matrices, in the sense of Hermitian matrices. And
so this is like the defined case that in general is just a Hermitian, but you can reduce it to unitary with a transformation which is Hermitian or unitary?
No, it is Hermitian. It's not a unitary matrix. No, this is a matrix indexed by its finite matrix, indexed by say a sequence of elements in the group, and you ask that it is it's not unitary. It should be. No. Sorry. Then it was a mistake. Yeah, I mean Hermitian. It should be positive. There is no positive unitary matrix. This doesn't make sense. I mean, so it should be a positive matrix. In the sense, not the positive entries, but the self-adjoint positive matrix. Yeah, okay. Okay, so
you mean that the eigenvalues are positive?
Yes, if you want. If you reduce it, then the eigenvalues are positive. Or the quadratic form that you can associate to the matrix is a positive quadratic form. Yes, it has to be an Hermitian. It has to be positive, so in particular it is a Hermitian. That's contained in the definition of positive, I would say. Okay, So what is the use of such function is that if you have such a function, you can look at on a group G, you can look at maybe not the L2 space, the space of function on the group, or if you want the group, or the group algebra, if you want, that the functions which are zero almost everywhere, that is except on a set of finite subsets of the group. These functions, you can let the group act on it by left or right regular representation. And then this function allows you to put an inner product. So with this function, the positive type function, you can put an inner product on this space. And this inner product will be invariant on the I don't know, probably the right representation. But if not, it's left. But okay, one of the two representation. And then in this way, you can build a unitary representation of the group. And any unitary representation, and this will be a coefficient of the unitary representation, and any unitary representation can correspond to a positive type function in this way. Okay. And now I will be interested in central positive type function. So a central function means just that the function is constant on conjugacy classes, or if you want, this is equal to, okay, on the group. Okay, if I have a central positive type function, then what I said is that in the case of the finite groups, these central positive type functions, they form I assume they are normalized. They form a convex set. Okay. And the extreme points of this convex set are exactly the irreducible characters. Okay, so extreme points of, let me call it P of G. P is a set of central positive type functions which are normalized. So the extreme points of this set are the normalized characters, irreducible characters. So the characters of the irreducible representation of the group and normalized, so I divide by the dimension, so that evaluated on the identity, it is always equal to 1.
Excuse me, this is the definition of irreducible characters for non-finite groups.
No, this is a theorem, if you want. So I stated the theorem in my first lecture. It's not difficult to prove, but it's...
Now we are in the infinite case.
Oh, no, I said that... oh, no, okay, so that's finite group, sorry. Okay. No, for the finite group, we have this. For infinite groups, it's more complicated because we don't know. In general, if you have an infinite group, it will have infinite dimensional representation. It will have very few finite dimensional representation. Most of its representation will be infinite dimensional. And then we don't know how to make sense of what is the trace, for example. In general, the trace of the unitary operators will not be defined. In infinite dimension, it's not defined in general. So you don't know how to, you cannot use the same theory because of that. Because in infinite dimension, everything will diverge. So, but on the other hand, this makes sense. The set of central positive type function, it is still a convex set, and you can still look at its extreme points of this convex set. There are some kind of substitute for the irreducible characters of unitary representations. In infinite dimension, also, for infinite group, not every representation will be unitary in general. You will have a lot of representations which are not unitary. So I said the theory is much more complicated.
And the non-central ones are just useless for the
No. You can define unitary representation, and okay. So then you can classify. I don't want to go into this theory. I'm not a specialist myself, but you can classify representation into type 2, type 3, and so on. These essentially are type 2 representations. They have a trace. They have a central. They correspond to some central positive type function. But you may have positive type function which do not correspond to type 2 representation. You may have type 3 and so on. So it can be very complicated theory and much more difficult analytically than the theory of finite groups. Okay.
Very nice question.
Yes, of course, of course. So what I say is that extreme points of P of G. So now my group G is infinite. Huh? Okay, so I look at the central positive type function. So the extreme points are called, so they are associated to unitary representation by the construction. I said, okay, you have this function, you can put an inner product on this space, you can complete it to a Hilbert space and extend the representation. It will give you a unitary representation on some infinite dimensional Hilbert space in general. And the extreme points, so they are called a factor representation or factor, or are associated with factor representations. So what does this mean? This means that if you look at the algebra generated by the representation, so in infinite dimension, if you have a finite group and you have an irreducible representation, the algebra generated by the representation, the matrices representing the group, is a set of all endomorphisms of your space. Okay, so this is what I said. If you have your space V, it corresponds to an irreducible representation of the space. Then the algebra generated by all the elements of all the matrices in the representation generates the whole algebra of endomorphism of V. This is no more true here. In general, if you have a factor representation, its commutant will, in general, be very large, also infinite dimensional. And but the representation will be vector, which means that is the center. So if I look at the group algebra, and so I need to close it. I take its image under the representation, and so I have to close it under some weak topology, okay, to get a fundamental algebra. And I can look at it, and then I can look at the center of this algebra, and the center will be equal to the multiple of the identity. So this is for this kind of representation. They are characterized by the fact that the center of the representation is reduced to the identity. It is trivial. But on the other hand, this algebra will not be equal to the whole algebra. It will have a very large commutant. Well, in fact, there is an intuitive way of thinking about this, which is the following. So you look. Suppose you are in the situation of the of your finite group, say the symmetric group. You are trying to do the following thing. So you take a character of an irreducible character. You use it on the L2 space of G. You produce some Hilbert space using this character on G, and this this Hilbert space product will single out so if chi is associated to lambda, it will single out the component corresponding to the irreducible representation. But we know that it is this component has a multiplicity which is equal to its dimension. That's true for any finite group actually. Okay, so we'll have this space. Okay, and what we are doing by this construction is constructing the representation, but in this space. So in this space, it is not irreducible. It has a multiplicity which is equal to its dimension. Okay? So what happens when the dimension will go to infinity? So this space will go to dimension will go to infinity. Dimension will go to infinity. So what happens is that in this finite dimensional case, it's not a big deal because we can always single out a vector here. So we take an orthogonal projection on a one-dimensional space.
What do you mean by single out?
So what I said is that G acts here, but we know that G acts also here. There is a left regular representation, the right regular representation. Okay, so J acts by the left representation on that, trivially on this thing, and by the right representation on that, and trivially on this factor, as we have seen. So there is a huge commutant. See, if I look just at the representation here, there is a huge commutant which is generated by this representation. Okay, but I say I can always find a subspace in this big space where my representation is irreducible, because I take projection on a one-dimensional subspace in the commutant. That is, here I will take a projection P on some vector, take any vector in this, any one-dimensional subspace in this space, take a projector which belongs to the algebra here. And if you take this, so since this projector will commute this with a representation, what you obtain is a representation here which is irreducible. The point is that in infinite dimensional, you cannot, in general, you cannot do that because there will be no, in the commutant, there will be no projection of, there will be no projection on one-dimensional subspaces. All the projection will be on infinite dimensional subspaces. Okay, if, it's not easy to see, but I just give you an intuitive picture of what happens. Suppose you have a set of endpoints, an interval, 1n, okay? Okay, so you can always take a point. Okay, but now, suppose you have an interval, 0, 1. Okay, you can take a point, but every point has 0 measure, so you don't see it. Because essentially what you are doing here, you are taking closures, and essentially it is the analog in this discrete situation of taking the closure with respect to the Lebesgue measure. So you are just looking at L infinity of this measure space. So you cannot see individual points. So there is no, if you want, in the algebra of measurable function on the interval 0, 1, there is no one-dimensional projection. All the projections are infinite dimensional. They correspond to indicator function of subspace with positive measure, so they are infinite dimensional. And an analogous thing occurs in the infinite limit, which is here. That is why the situation is more complicated. You have to use other tools than just linear algebra. You just need to use von Neumann algebras and things like that. So the situation is more complicated, okay, in this sense. But here, I will just be interested in describing this set here. So there is a very nice description of this set. It's a theorem which was found in the 60s by Thomas. So I will describe now Thomas' theorem. That's L2 instead of infinity. They are not useful for describing when describing the indicator function of a measurable subset using the Fourier series. It can be very nasty. I mean, and I mean, it's not what you. I mean, it's not useful in this context. I mean. So, what is Thomas' theorem? So the question is the following. So you look at the central positive type function on your group, which is S infinity in this case, and you want to describe this function, the extremal points in this convex set. Okay. So the first is that extremal positive type functions on S infinity, and I said central and normalized. On infinity are multiplicative. That's the first statement. This means that if I have such a function, phi if sigma 1 and sigma 2 have disjoint support. So what does this mean? That means if I have a permutation, so it's a finite permutation of S infinity, so it moves a certain finite set of points, and so it's a permutation of this finite subset. And sigma 2 also can be considered as a permutation of a finite subset of the positive integers. And the support is just the set that the points that are moved, that is the points which belong to a cycle of length larger than 2. Okay, in the cyclic decomposition of sigma. Okay, so this is so the first statement is that if I am in a such situation that I have two permutations which have a disjoint support, so they don't move the same points, then the function is multiplicative. It's not difficult to understand why, but if you have to assume something, the following thing, which is a very general thing, if you have a product of two groups, okay, say two countable groups or even final, you have a product of two groups, then you can look at the set of P of G1, P of G2, and you can set, so the set of positive type central, etc., function on G1, on G2, and you can take the extremal ones. Okay? And the claim is that this is equal to the set of extremal points of G1 times G2. That is, any extremal function, extreme positive type, central, etc., function on the product of group is actually the product of its restriction to each of the subgroups which are here. Okay, so this is a very general fact that it is not too difficult to see. And well, if you apply this here, you can see that S infinity, it contains copies of itself times itself. It's take two infinite subsets of the positive integers. Okay, so you can always see that in S infinity you contain copies of. Okay, so if you have a you apply this result here, and so you take some copy of S infinity which contains sigma 1, some copy of S infinity which contains sigma 2, and you apply the result here. And you see that phi, of course, phi of sigma 1 is the same phi because it is just the restriction. So this general property is something which is just results from the fact that S infinity times S infinity is included into S infinity. Okay, you have many ways to see that, but what?
Is it equal? No.
Equal what?
To S infinity.
Oh, this equality?
Yes.
No, it is not equal. In general, if you take a subset, you always have permutation which mix the two subsets. Certainly, it's not equal. It is in general much smaller. It's infinitely smaller, I would say. I mean,
in several ways, or in every way you can.
yeah, yes, there are many such embeddings, and okay, but the existence of at least one is enough to conclude, you need enough to conclude. That. That's all.
Sorry,
Yeah?
the extremal central normalized, what you wrote, you wrote an equality, but I guess it's an isomorphism.
Yes, I mean you can put topologies, and it's yes. You can, if you want, you can put topologies on that, and then if you have a countable group, you can put the topology of simple convergence on the set of such functions, and then it gives you a compact space. That's important because then you want to do, then yes, there is also a theorem that every positive type function, which is central, is an integral of extremal positive in a unique way, an integral over the set of extreme points. So it's a simplex, in fact. It's a simplex. A simplex means a convex set in which every point inside can be is the barycenter of a unique measure which is supported on the outside, on the extreme points. Like a triangle or a tetrahedron. Okay.
So that equality, you mean homeomorphism?
Yeah.
A stupid question. I don't know why you just said that. How are done the conjugacy classes in S infinity?
How?
The conjugacy classes in S infinity.
Yeah.
Are they finite or infinite?
Oh, infinite, of course. You have infinitely many transpositions in S infinity. There are many of them.
So, except for the identity.
Yes.
How do you understand it?
Yes. This means that what you just noticed is that the regular representation is a factor representation in this case. The regular representation, if you close it, I will not explain. Using the trivial, the character of the regular representation, you get a factor representation. That is, the Feynman algebra generated by this representation has no non-trivial element. It is just composed of the multiples identity. Because all infinite conjugacy classes are infinite, so they are not finite support, so they cannot be approximated by things in the fundamental algebra. Okay, so that's so you see, it's at first it's a bit difficult to grasp what happened in infinite dimension, okay? Because it's different from what? Of course, the conjugacy classes are exactly what you expect. I mean, you are just a finite set of non-trivial cycles and an infinite set of fixed points. That's all. The conjugacy classes are obviously the same as what we get. They are indexed by partitions, but partitions with an infinite number of ones. Okay. Okay. So that's the first part of Thomas' theorem. So this means that if you have a permutation sigma, then you can decompose it into cycles, and then if you want to find phi of sigma, you just need to evaluate it on the cycle. So what is the value on the cycle? So what is the value on the cycle? So the answer is that so we can describe all the positive type extremal function by just give this set of numbers, okay? And the answer is that there exists a sequence of numbers, real numbers, positive real numbers. There exists another sequence of real numbers. Okay. And so for each so for each phi, there is such a function, such a pair. So the sum of alpha I plus the sum of beta I is smaller than 1, at most 1. And if I have a non-trivial cycle here, this is equal to the sum of alpha I to the k plus minus 1 to the k minus 1 beta I to the k. I think it's k minus 1 probably, and I think the formula seems to be. What?
Minus 1 to the k.
No. That's very important. Okay, so there exists such a pair of sequences of real numbers. Their sum have to be equal to 1, smaller than 1. Sorry. Or you can introduce gamma, which is it is sometimes interesting to introduce this number gamma, which has to be positive. So it's a third parameter, but it is determined by the sequences of parameters. And you see in particular, so this is a very special form of all the positive type function on the extremal ones on the infinite symmetry group. And you see that, well, this is equal to the integral of x to the k minus 1. Is it k minus 1 or? So is k is equal to 2? Yes. Yes. I'm trying to get it right because because there is always something between k and k minus 1. So I want to be sure to write down the good formula. I think it's k minus. It should be k minus 1. So.
Gamma does not depend on k. Gamma, does it depend on k?
No. Here you see gamma. It depends on the numbers alpha and beta.
So don't you have that plus gamma Kronecker delta kappa 1?
So the idea is that so phi on a cycle of length k. We will see why very quickly. It is the integral of, I think it's x to the k minus 1 d mu of x, and mu is it's a probability measure. It's the sum of alpha I delta alpha I plus beta I delta minus beta I plus gamma delta 0. Okay, so you have, so it's a sum of the I here. Okay, you have a sum of Dirac measures on some real numbers, alpha I, which are between 0 and 1. You have some Dirac mass with some mass here on the points which are negative, minus beta I. And you have a mass at 0, which is here. And the correct formula is this one. So I think it's it should be K's and -1 here. Yes, I think that's the correct. Seems to be the correct formula. What? No. Delta 0. You never count delta 0 when you look at moments, because K is larger than 1, so it never counts. Of course, if you take this here is just so that you get the probability measure. That's all. But we will see what is the significance of that and why this is okay. And we will see how it is related to what I said. Okay. Okay. So this is Thomas' theorem, and the great insight of Kerhoff and Ferschik was to understand that this theorem about S infinity is in fact, you can see it as the limit of what happens in Sn, as n goes to infinity. But then you have to understand where these numbers, alpha I and beta I and gamma, they come from. Okay? In the theory of Thomas, they just come out of some result in analysis. They just like a rabbit out of a hat. You don't see any significance to these numbers. And it was Kerhoff and Ferschik who understood a few years later after. So the theorem of Thomas is, I think, in the 60s. Goes back to the 60s. And then in the 70s and the 80s, Kerhoff and Ferschik investigated the infinite limit of the representation theory of Sn, and they understood what these numbers represent here. Okay? And so this is what I'm going to explain now. You have such numbers? Yes. And so the set, if you want, I can describe this set, EP of G. It is called yes, let me write it here. I introduce the Thomas simplex. So I call it T. It's a set of, say, so with alpha okay, and with if you want, you can add gamma, but it's not gamma is not really. I mean, it does not add any more information, and such that the sigma of alpha I plus sigma beta I plus gamma is equal to 1. So this is the Thomas simplex. It's a topological space, a compact topological space. If you look at the convergence, simple convergence, it's a compact. So there are some things which are a bit tricky here. So, for example, there is a subspace. So gamma equals 0. If you want the subspace corresponding to gamma equals 0, it is the one such that sigma of alpha is equal plus sigma of beta is equal to 1. Okay? But this subset, it's not closed. Actually, it is dense in the Thomas simplex. Yes, because you know, suppose take any sequence like that with some gamma strictly positive. Okay, so you can always add some points here, very small points which add to gamma. Many of them say n points which are equal to gamma over n, and put them in the list of alpha. Okay, and then the sum of alpha and beta will be equal to 1. But when n go to infinity, all these points will go to 0. Okay, so in the end, you will converge towards point sequence like that with only sequences satisfying that. Okay? Yes. Yes, point-weight convergence on the alpha I and the beta I and the coordinates. Okay? So you see that gamma is not a continuous function. So it's a bit tricky. So you have to notice that before you. And maybe you can embed this into probability measures by this map here. You can embed it into probability measures on the interval -1 + 1, and then this is a continuous embedding. It is continuous and homeomorphic. And you see that in this, you cannot find delta. You see that delta 0 it's not something continuous. I mean, finding the mass of 0, you cannot express this in a continuous way on the space of measures.
So, when gamma is equal to 1 and all the alpha beta are absent,
on the other hand, there are obvious inequalities on the alpha I. For example, alpha 1 is smaller than 1, alpha 2 is smaller than 1/2, alpha 3 is smaller than 1/3. And so on. So in any finite interval out of 0, you have only finitely many points. Okay. So this means that these points you can if you are given just the measures, you can easily spot these points. But what happens near 0 is a bit of a mess. Okay. So for example, if you are given the moments, in principle you can find if you are given the moments, you can recover the measure because it's a compact supported measure. So the moments of this measure, so in particular the moments which are these numbers here, they completely determine the sequence, alpha and beta. But if you are given, say, a finite number, a large number, but finite number of moments, you can give a good approximation of alpha 1, alpha 2, but near 0 you don't know, you don't see anything. I mean.
So cutting out a neighborhood of 0 somehow corresponds to looking at the finite Sn?
I will explain what it means in a moment. Okay. So. So I'm going to do something now. I'm going to put another set of coordinates on the set of Young diagrams. So let me take a diagram like that. So in each such diagram, there is some square inside, maximal square. Just go along this diagonal here, along this line until you exit the diagram, and then there is some there is some partition here. There is some partition here. Like that. Okay, so a typical diagram looks like that. There is a square, the maximal square, and one way to parameterize. Okay, we have seen that there is one way to parameterize the partition, which is to give the length of the columns. So lambda 1 larger than lambda 2. Okay. Another way is to give to look at the transpose partition. The transpose partition is just you make a flip with respect to the symmetries with respect to the vertical axis. It is called the conjugate partition, and it has also a list lambda prime 1, lambda prime 2, and so on. Okay, so these are the lengths of the lines of the partition or the columns of the partition, if you want. Okay, and there is another way to parameterize it. It is to look at the length here, but to stop. So there are some squares here, and what you do is you look at the lengths which are here. It's a sequence of lengths. Okay, and you can parameterize, obviously, the diagram by giving all the lengths which are here. So here I will have some numbers, Q1, minus Q1, smaller than minus Q2, etc. Actually, there is a strict inequality. Sorry. If you want a geometric picture of that, so these are called essentially the Frobenius coordinates. I will give a precise definition because, okay, you may, okay, there is some ambiguity. Sometimes you can have, sometimes, for example, you can take this length here. So the first is lambda minus 1, but then it is convenient to add so it is the surface of this here. Where you don't use this square. But now you are going to use this square, half of it on the right, half of it on the left, so you may want to add 1/2 like that to define, say, P1. P1 will be the largest number here, P1, then P2, etc. Another way to see that is to look at the function, this diagram, as the graph of a function. And you see that the p's will be exactly the coordinates of the middle of the points, of the intervals where you have a decreasing, on the left of 0, and on the right on the increasing segments. Okay, the middle of the coordinates of the increasing segment. Okay, so you get two sequences of numbers, so like that, strictly increasing, and okay. And there is the same number of such numbers, which is R, which is just the size of the square, which is here. Okay, so it's a way to encode the partition by two sets of positive numbers, distinct positive numbers. Okay, and what? Yes. The q's again. The q's are the length here plus the 1/2 for the square, which is here. At the end, I want sigma of qi plus sigma of pi equal n, the number of boxes. Okay. So I really have to. If not, then I would have to. It would be a bit nasty. I would have to take out this the diagonal here, the surface of the diagonal. So by taking half integers, I have this nice formula. But in the yeah.
You cut the box in the middle in two, right?
What?
You cut the middle boxes in two.
Yes. Yes. 1/2 of the surface. So from that, it is obvious that the sum is equal to the surface, total surface, which is n. Okay. Or n, or well, I mean the surface. Assuming that the surface of each square is equal to 1, because with my convention there would be some 2 factors, square root of 2. I don't want. Okay. If you want these numbers here to be integers, then you have to make.
You can make the 1/2.
Yeah. Okay. Don't worry. It's easy to see on the diagram, but if you want to write it down, then you will make all of kind of just nonsense. Because of these little things. But anyhow, it's not very important because we are going to reduce this diagram by a factor n. And so the 1/2 will play absolutely no role in the limit. Okay, we will just forget about it. Okay. So now I have the Frobenius coordinate. And what I will do, I will embed the set of partitions of n. Let me call P of n the set of partitions of n. So it is the set of, if you want, irreducible characters of the symmetric group of Sn. I will embed it into the Thomas simplex. In a very simple way, I will say that it is just given by the two sequences. So the sequence, of course, is finite. It is 0 after some point. And Q1. Okay. Since the sum is equal to n here, I see that really this belongs to the Thomas simplex, and it belongs to the subspace, the dense subspace that I have spotted there, where the sum of the coordinates is equal to 1. So gamma equals 0. It belongs to the subspace where gamma equals to 0. Okay. But we have seen it is a dense subset. Okay. And now, claim. If I look, so for each lambda in Pn, P of n, so a partition. So I can associate an element in the Thomas simplex, and I said that I could also associate a probability measure on the real line, which is given by the distribution of the Justice Murphy element. Okay, there is a cotransition measure. Okay. Now, what I will do, I will make a scaling in the in the diagram. So I will remember my formula for the co-transition measure. Okay, so yes, now I realize that I should have told you something. I thought I didn't need it now, but I need it now. So I will make a few remarks because, you know, I had this formula. You look at, so remember this formula for the co-transition measure. So it is a probability measure. So when I have two sequences of interlacing integers, the y's and the x, this defines me a probability measure on the x, on the set of x's. And what I need is just two sequences of interlacing integers, so y1, okay, so now there is some condition because not all these two sequences can occur as the maxima and minima of such a graph. So what I claim is the following. I claim first that the sigma of xi, the sum of the x is equal to the sum of the y's. And second, that n, the number of boxes that I have in my partition, is equal to E2 of x minus E2 of y. E2 is just the second elementary symmetric function, that is the sum of xi, xj, and here the sum of yi, yj. Okay? So this is not difficult to check. So what you can do is and these things actually continue to hold if the xi and yi are arbitrary real numbers. I mean, you can define this. If you have a sequence of arbitrary real numbers satisfying this condition here, you can define this probability measure by putting as n here this difference, which is here. So n will be if you want, it is the surface of your graph. Of the graph which is behind, below the function and above this points here. Quelle heure est-il là? Ah oui, d'accord. J'ai pas fait ma pause. Okay, so I make a break because I think it's a bit tiring. So in 3 minutes, I will explain these two things, which is simple observations. Or I leave it as an exercise. Homework. What? To prove that if you describe a function like that using the local minima and local maxima, then you have this equality between sum of the x and sums of the y's, and then prove that the surface of the curve, below the curve and above this wedge, is equal to this quantity. Hmm? Yeah, if you want. You can see it also. Well, one way to see it is to approximate, is to make see that this is invariant by some scaling, and approximate any real numbers by integers, by rationals. Then you see that if this is a probability measure, it will remain a probability measure on the scaling and approximation. It's not very elegant, but it works. I mean, if you know it for... but of course, it's simple. I mean, you can see it also directly. I mean, I will show you, but not this time because it will take me some time. But next time I will show you why it's true.
It's really important that n is a quadratic function of x and y because we
Yeah.
have two more factors in numerator than in
Yes, of course.
otherwise it cannot be scaled.
No. Certainly. Huh? That's part of the exercise. This proves that it is a probability measure.
Okay. So what's
What? What is?
how can you figure out what n is in the general form?
It is a surface. You have this curve, and you have below, like in the case of the partition, it's a surface of the, which is between your wedge and between the thing.
So this is the solvent.
Yes, it is. The resolvent is given explicitly in this. Because the x and the y alternate, when you do the expansion, you have positive weights. And the sum is equal to 1 because of the second formula there. When you expand at infinity, you see that it's equivalent to 1 over z. When you expand at infinity. You see there is degree 1 more above than below, so you subtract z. And the second term is 0 because of the first line. And then when you divide by n, by the second line, you get that in the expansion you get 1 over z, it's 1 over z at infinity. So it's really some resolvent of some probability measure.
About alpha and beta and gamma being also related to positivity or technology.
Related to? Oh yes. This is related to also to Schur function. Yes, certainly.
You said that on
No. Probably I will not talk about that. I will say a few words later. But, it's an exercise. It's a condition. If you have such a graph, necessarily the sum of the y's. You see, if you are given the first y and x, the last one y is determined because you go there. So there has to be a relation.
This is a condition on the
Yeah.
sequence.
Yes.
You have to be able to make sense of the right.
Yes. It has to end exactly at a point on these two things. So there is some condition that you need to. It's not an arbitrary sequence of numbers, interlacing. And I mean, and it's not very difficult to prove by induction on the number of points because when you add up, when you add a square, yeah, you just add a square in the middle and you check that everything remains true, and it's true if you have 3 points. That's clear, very easy to check, and then you add some small squares inside, and then you divide in induction. It's a 2-line computation. So. Yeah.
I see that you're gonna have issue of y.
I'm going to have.
Tu fais l'expansion
Oui.
du produit. Je vois bien que tu vas avoir E2 de y. Mais pourquoi tu n'as pas H2 de x?
Je n'ai pas H2.
H2 parce que E2. Parce que x est dénominateur.
Oui.
Et donc, tu peux aussi
Non, mais tu
avoir
dois enlever z. Tu dois enlever z. Tu réduis au même dénominateur, tu as z fois le truc de x qui apparaît. Tu regardes le terme de plus haut degré, c'est z puissance n. Z puissance n plus 1. Ensuite, ou z puissance r, disons. Et ensuite, tu as... oui, non, j'ai fait une erreur, c'est y r plus 1.
C'est z puissance n plus 1, série n1 sur z de E1, E2, E3, E4 de y. Et pour le dénominateur, c'est la même chose, z à la puissance n. Mais la série, c'est avec des h.
Ouais.
Donc, je vais contrôler à tous degrés. Ça sera les premiers termes qui sont nuls, les deuxièmes.
Le premier terme, c'est z puissance n. Le deuxième, c'est le E1 et E1. E1 de x égale E1 de y.
Mais le deuxième, c'est
E2 de x moins E2 de y. Non, c'est le terme...
H de y.
Où est-ce que tu vois un h? Qu'est-ce que c'est h?
Quand je fais l'expansion de Taylor de 1 sur z moins x,
Mais il ne faut pas faire ça. Il faut pas faire ça. Il faut réduire au même dénominateur. Tu as 2 polynômes au numérateur. et tu les... Tu as deux polynômes non numérateurs et tu les réduis. Les termes de plus haut degré s'en vont, les termes de degré suivant s'en vont à cause de 1. Le terme suivant, c'est n fois quelque chose. Et tu as divisé, ensuite tu divises par n, c'est tout. OK. Okay, so let's continue. So my exercise, so first there was a mistake here. There is one more y than x, okay, clearly. And second, essentially, what I claim is that if you take the CGS transform of the measure, which is this quantity here, what you get is this formula. And this formula holds in general when n is equal to be this here. Okay, but I leave this as an exercise, and the hint is that first check if you have y1, x1, y2, then it is a very simple exercise. You just have a rectangle, okay? And then do induction. And you see that you can build a partition by, you start with a rectangle like that, and then you add a rectangle somewhere, or somewhere, etc. And you fill in by rectangles. That means you replace one of the x's by a triple y, x, y, okay? You replace the x which is here by the three numbers which are here, okay? And it is easy to see that you can build the thing, and that by induction you can prove all these things which are here. So I will come back to these formulas later when we study the transition measure this time. There will be close connection between the two. Okay, so these were some facts about the cotransition measure. Okay, so now. Okay, so sorry, I was there. So I was going to claim something. So what I was using that to say that I can scale my diagram by n, which means that I divide the numbers x, y by n here, and then I get a new probability measure, okay, which is just the other one scaled by a factor n. Okay, I take the same things here, and I get the same probability measure. I get a new probability measure, which is this time supported on points xi, which are between -1 and +1. Okay? Because of course the x are between -n and n in general, and when you scale by a factor n, 1 over n, you get points which are between -1 and +1. So I can define this for each lambda in the probability measure. So which means that I said that I embedded Pn in tau, and what I claim is that if n goes to infinity and lambda n, so I have a sequence of integers. Let me call them n, but I don't need to have it defined for any n. It's just I suppose that lambda, I take a partition of n, and I assume that this goes to some omega in the Thomas simplex.
If you divide every xi and yj by n, and
yeah.
you have a different amount of factors in your fraction,
yeah.
you should renormalize.
Yes, you should.
Yes,
you should renormalize this formula. So, and this is why I showed you this exercise, small exercise. Okay. You have to renormalize it. What? 1 over n. Well, I have used this embedding. So an element of P of n. I embed it into I look at it. Of course, I have made n scaling here. So I see it as a point in the Thomas simplex. Okay? And I said that when n goes to infinity, this may converge. Certainly, any sequence will have a subsequence which converges to some point in the Thomas simplex. Certainly, because it's a compact space. Okay? Okay, so, and assume so that I take some sequence which converges to a point omega in the Thomas simplex. Then, what I claim is that the cotransition measure of my so my thing, converges to the probability measure associated with omega, the element in the Thomas simplex. So I wrote this formula, the sum of the alpha I, delta alpha I, and so on. Okay? This is a probability measure supported on -1 + 1, which is atomic probability measure. And what I claim is that I have convergence of these probability measures. Okay, so we have to check that. So how do we do?
So actually, if anything survives
Mm-hmm.
in alpha and beta,
Mm-hmm.
then the X and Y stick together in small diamonds and then run away by big gaps.
Yeah. Yeah. What I claim is that if this holds true, then P1 over n should converge to alpha 1, P2 over n should converge to alpha 2, and so on. And Q1 over n should converge to beta 1. This is exactly what it means, that there is convergence in this space. Okay? So by hypothesis, so P1 over n converges to alpha 1. This is my hypothesis, okay? And same for and so on, okay? This is the idea. And I know that any element in the Thomas simplex can be obtained as a limit. Okay, it's not difficult to check that any element in the Thomas simplex is the limit of some sequence of partitions in this sense. Okay, a limit of some sequence of elements in P of n. Okay, not difficult to. So this means that if I have, so what does my very large partition look like? Well, the first column. So if this is true, then of course, etc. Okay, because these numbers differ only by a finite quantity, and so when you divide by n, everything is okay. And the same is true here, lambda prime 1, etc. Okay, so these things are of course equivalent. Okay, but the point is that you cannot use lambda 1, lambda n, and lambda prime 1, lambda prime n to embed this into the Thomas simplex because you would have a sum which is too large. Okay, so you don't want to do that. It's just a matter of convenience. Okay, so this means you have a very, very long first row, which is here. Then you have a very, very long second row, which is here. And so on. And same on the other side. You have a very long column of the partition. Second column also, which is very long. And so on. Okay? So this is a general picture. When you converge to a point in the Thomas simplex, you have partitions which are very, very long rows and columns. Okay? So, so what I prove, and so for such, okay, so there are some difficulties if what I will prove is that the mu of, so let me call this, so this is, so let me look now at the transition measure, the co-transition measure. So what I need to look at is, so here I have y1, which is here, and x1 is, so it's yr, and yr plus 1, xr plus 1. So here I have some yr and yr minus 1, and so on. And here I have y1, x1, and so on. Okay? That's xr. The x are on the left each time because they correspond to the local maxima, and the y are on the right because they correspond to local minima. Okay, so this is in. So what I'm going to prove is that the measure will be supported by point, which is if I scale by n, which is very close to alpha 1, alpha 2, alpha 3. So we just need to check that the weights of the measure converge to what we want. That's all. Okay. So this is a little computation. So there is a trick. There is something which is tricky. And I will assume here that, so I will prove it when alpha k is like that. So I will prove it, say, I will prove it for the beta. Of course, it's completely equivalent to prove it for the beta and the alpha. Okay, and the beta from a decreasing sequence. I will assume that the beta k has multiplicity 1 in the end, because we will see the proof is not very difficult. It's a bit more complicated if beta k has multiplicity more, because then we could have several points here which are clustering here, and some of them may be equal or not, and this changes a bit the formula. So it's a bit of a mess if you want to write it, especially on a blackboard. So I will just do this simple case, okay? And I mean, it's not difficult to see that the general case holds by similar reasoning. So. Okay, so let us make this assumption. So at some point, I have some point xk which is here, and so the point which is here, which is xk minus 1, and some point here which is say xk plus 1, and of course here yk is equal to, in this case, yk is equal to xk minus 1. Okay, so I assume that I have my n is large enough, so that I have a very good approximation of the first L, beta, alpha, and beta. So that means that, say, P1 over n minus alpha 1 is small, okay? And up to PL over n minus alpha L is small. And same thing for the Q. Q1 over n minus beta 1 is small, and QL over n minus beta L is small. So I choose a large n, I choose a small epsilon, okay? And you see that here I have a bound which is that beta L is smaller than 1 over L, okay? So this means that all the so I assume that so my first point on the left and on the right, they are very well approximated by lambda. But then in the middle, there is some mess, but I don't care because it is in a very small interval of width 1 over L. Okay, so there is some interval here, 1 over L. Look, I have no control about what happens here. Okay, but I have very good control on what happens outside. And I assume that all these things are small. All the differences are small. Okay? Okay? I can always assume that because I have this convergence here. Okay? So I assume that all the coordinates converge. Okay. And now, well, I have to compute the probability of x according to the cotransition measure. So how is it? So mu of xk, it is 1 over n, the product of the, so that's, okay, so I have rescaled by, okay, so this is my large partition. I will use the not scaled partition, and yes. Yes. Mu is a measure of the point xk under the transition probability, the cotransition probability, and I know that xk is very close to n times beta k here.
Yeah, but it's annoying the fact that xk is really there, but it's not a notion. I mean, when you take the subsequence of lambdas,
yeah,
they're moving all the time.
Of course, yes, of course.
You're really looking at the measure, not the
Yes, but I mean, this is a compact space, and so I can always extract convergence subsequence, and of course, xk will not be equal to n times alpha k. There's no reason. It will just be close. That's the only thing I can assume.
So you are implicitly multiplying mu by some test function which is concentrated.
No, I said that what I say is that certainly this is true. if I compute all moments of these measures, they will they will converge, and so.
In appropriate space.
Yeah. In the usual convergence of measures, I mean, it's just. Yeah. I mean, if you have so if I have some factor here, say R and K, I want to prove that it converges to the factor here converges to alpha K. That's what I want to prove. And for this, I have to do this this product here. Okay, so in this product, I will take the first L product. I will take the product from J equal 1 to L, xk minus yj. Okay, I have the product. I have a product of all the y which are in the middle, and then I have the product of the last ones. Say the product from J equal R minus L. Of xk minus yj. And I do the same here. I have a product from J equal 1.
J from R minus L to R1.
What?
From R minus L to R.
Oh, sorry. Yeah, yes. Yes, the last terms. Okay. To R. Yes, you're right. Okay, thank you. That's true. I look at the last ones. And these ones I can control very well because I have all these things here. And no, what I claim is that the everything extreme goes to you can pair the thing so that because yj essentially is equal to xj up to 1. So if I divide everything by n, everything goes to 0 to 1. Sorry, the quotient goes to 1.
In the denominator, you have said that k is smaller than capital L.
Yes, of course. Yes, k is smaller than capital L. Yes.
It's a case analysis.
No. I want to prove that. So I can choose some L which is very large and some epsilon which is very small. I first choose L and then I choose epsilon so that all these things are true and it's possible. Okay. So what I claim is that here essentially there is one. Okay. So what I claim is that this and this, the quotients, they are close to 1.
You have the factor 1 over that.
Hmm?
The factor 1
so you say there is one more factor above than here, but the factor is xk minus yk, but it is equal to 1.
No, I mean from before you forgot the factor 1 over that.
Oh yes, there is some factor here, 1 over n, you're right. What I claim is that this and this, essentially you can replace xk by its approximation and divide everything by n and you see. So there is one factor which is tricky, which is xk minus yk, but this is equal to 1, essentially. Because, yes?
Yj in the denominator as well? Yes, there's a typo over that. What's the way the last character xj?
This is xj. Oh, sorry, yeah, of course. Sorry.
And also in your blog, you don't mean to include the factor before last, right? Okay, in between remains. Yeah, the blog, there's a...
Oh, yeah, there is a factor here. Yes.
No, but you included it. You shouldn't include it in the blog.
Oh, yeah, sorry. Yeah. I wrote it, but I made, okay. I should draw the picture. Okay, right, thank you. Okay, so now everything is in this. Okay. So I think probably it's here it's a +1, okay? Because I have to always to pair. On the right, I have to pair j plus 1 with j. So it's probably something like that, okay? So I'm just pairing the y and with the x, which is very close to it, okay?
The last number is y sub r plus 1, so the product should go to up to r, not to r minus 1.
Yes. Upstairs.
The last index of y should be r plus 1.
Oh, yes, you're right. Yes, okay. Anyhow, you just look on the picture. You just you're just pairing the x and the y here, and you're just looking at the quotient. It's a product of numbers which are essentially 1, very close to 1. So this is essentially, you can make it very close to 1. So there remain the things in the middle. And the things in the middle, so I expand a little my graph. So there is this thing here. So I have some, so xk is here. Okay. And, okay, so let's say xl is here. And so in the middle, I have something which is, y, say yl is here. So yl plus 1 maybe. Okay, and in the middle, and I have, so everything on the right of that and on the left of that is control. Essentially, it gives you 1 in the. And here I have something complicated, where I have products of terms which are so there is one more term above than in the below, because you count there is one more y than x's. I have paired all the y's and the x's outside this interval, but inside the interval I have one more y than x. So I write it like that. So it's the first term is xk minus, say, what it should be, xl plus 1 over, that's the first I get. No, it should be probably the other way around. Above. Okay, yes, you're right. Yes, okay. So I have products of y's. Y, so that's r minus l plus 1. Okay, there is some product of y's, and there is some product of x's, which are interlacing below. Okay, so don't worry about the indices. I think you understand what I mean. Something like that, okay? So there is one more y above than x's below, because I have paired the y's outside with the x's, so inside there is one more. And now we see that this, so all this, so I have a product. If I look at the product of the alternating in this way, so I am looking at a sequence which is increasing, and I am looking at the first term divided by a second, multiplied by the third, and so on. So certainly, the whole product should be larger than this one and smaller than the last one. Okay, because you have one term, and if you want, you multiply it by, you can group the terms like that, and all these terms here are larger than 1, the product. Or you can look at this term and group the term like that and multiply it by terms which are smaller than 1. Okay, so certainly we have, which is my quantity that I want to estimate, this quantity, big X, is between xk minus yl and xk minus y r minus l plus 1. Okay? But now if I divide by n, you see, I divide everything by n, because you remember I had an n here. Fortunately, I divide by n, so this really, this x over n is my probability, essentially, because everything else is close to 1. So the x over n. So now the YL is small because all these things are very close to 0. YL is smaller than 1 over L, and I have chosen a very large L. Okay, so certainly these things are close to xk over n, which is alpha k. Okay, so this proves the formula that I want. So this will converge. There are two quantities which converge to alpha k, and I am sandwiched between the two quantities. Okay.
So in fact, you are in the regime of the resolvent over there when z is
Yeah.
much outside of the measure. So you can cut out the long lines, and
Yeah.
you have a smaller diagram
Yeah.
for which you can study the resolvent.
Yeah. Maybe. Okay. Anyhow, is it clear for everybody the proof? I mean, it's just a computation. You have to check that your terms converge, and okay, yeah, you have to put epsilon everywhere. I didn't do it, but.
Much simpler to do the hook walk.
You want to do the hook walk?
Probability alpha I, it would be the I square, and the regime you're in, and it has to exit from the right.
Maybe. Maybe. Okay, that's an exercise for check that Guillaume's idea works. Okay, maybe, you're right. Okay, but here, I mean, the argument is not very difficult. I mean, you just have to see that this product is sandwiched between the two extremities, which is not very deep. I mean, just okay. So we see. So essentially, we have finished now because we have proved that the encore un quart d'heure. Okay. So what we have proved is that if I have a sequence which converges in the Thomas simplex, the associated measure, the co-translation measure, converges to the measure associated with the point in the Thomas simplex, the point omega. Okay. So as a consequence, I will show you that the possible limits of the extremal characters are given by the formula of Thomas. Thomas formula. So suppose you have a sequence of characters. Now you see that any character, irreducible character, defines a positive definite function, a positive type function on the group Sn. Okay. So if I have a limit, if any sequence indexed by n has some limit, the limit will be a positive type function on the infinite group, because for that you need to check only finite values. Okay. And so certainly any function if chi lambda of n converges to some chi, some function chi, then the limit here is a function on the S infinity, which is a positive type, because it is a limit of function. The function are not, say it is a limit of the function chi, which is with the indicator function of the smaller group Sn. But when I go to infinity, it will converge to some function on the whole group. And because I have only a finite conditions to check, certainly the limit will be positive type function. Okay? We will talk about that. Okay. The extremality is an issue, of course. But here, okay, so I have to, but then, what do I do? So I want to compute this on a cycle then. Okay. First is I want to compute this on a cycle. Well, if I compute an extremal, an irreducible on a cycle, then what I say is that essentially this is equal to the trace of Jn to the k minus 1. Maybe divided by n. Okay, so there is a law of large numbers. Say Jn is 1, 2, 1n plus, etc., plus n minus 1n. So it's a sum, if you want, of operators whose distribution in some sense is exchangeable. There you can exchange them. there are n-1 of them, so you can rescale it by n. Okay? And now, what I say is that this is the integral of x to the k-1 of the co-transition measure of my diagram, lambda of n, divided by n. Okay? I have made a scaling by n of everything because I have divided by jn by n. Okay? Okay. And so why is this true? Well, this is very simple. Take a typical, expand this product here, this power here. A typical element will look like okay? So you have to sum over all sequences, I1, I2, ik minus 1, where the i's are between 1 and minus 1. Okay? What I claim is that to first order, if n is going to infinity, all this, with probability going to 1, the I have to be distinct. Okay? So essentially, Jn to the k minus 1 is something like it's a conjugacy class. It's not a conjugacy class. It's a sum of cycles which contain of length k, which it's a sum of okay, where the okay, there is some combinatorial factor because of course any well, no, I think there's no combinatorial factor actually, and they don't have to be increasing. Sorry, they just have to be distinct. So it's a sum of all the cycles of length k, which contains the element n. Okay, and the number of them, of course, is a number of ways that you can get this. So it's n minus 1, n minus 2, etc. N minus k plus 1, probably, or n minus k. So 1, 2, there are k minus 1 of them. Okay. What? This number? Is the number of terms, yes. What? No, the number of terms here is equal to that. And I say this, and there are the terms. But now, if I compute the character on these terms, then all the terms are smaller than 1, certainly, each term, and their number is a smaller power of n. So here, it's essentially, it's like n to the k minus 1 times the character of the cycle of length k. If I evaluate the trace of that, okay, divided by if I divide by the dimensions, so this is a normalized character. So this is n to the k minus 1 times the character of ck. And I have other terms, but in the limit, they vanish, because the number of terms that I have is smaller than n to the, it's something like n to the k minus 2. So it's smaller, so it vanishes in the limit. And
you need some restriction on how big the trace can be?
On the?
How big the trace can be?
No, but it is a normalized trace. So k of any permutation is smaller than 1. It's I take the trace divided by the dimension. This is what I mean by this is this expression here. The trace divided by the dimension is the normalized character. So the normalized character if I evaluate it on that, it is equivalent to evaluate it on a cycle of length k. Okay, it gives asymptotically the same thing. And the reason for that is very simple. It's just that if you take k numbers at random, they will, in a large size, set of large size, they will be distinct with probability going to 1. That's all. Nothing deep behind that. I mean, okay. So we have this. So we see that, and now the co-transition measure. So this converges to the sigma of alpha I to the k minus 1, sigma of minus k. Okay. For k larger than 2. Hmm?
The result of the integral was the delta.
So I prove that this measure converges to the measure, so the moments converge. Okay. By what I prove, you can also prove directly the convergence of moments, because outside a small interval near zero, everything converges obviously, and near zero, the moments don't play no role. I mean, they are very small, so it's easy also to check that directly without. Okay, it's a simple computation.
Maybe another way of seeing that is to say that in large n, Jn to the k minus 1 is more or less like Jn, Jn minus 1, Jn minus k.
What do you mean, J?
Jn to the power.
It's Jn. What you mean, J minus 1? Is that you?
Minus 1 and
Ah. Oh no, it's not true. It's yeah. It's, they are not far. Okay. But why is it easier to use that than use that? Okay. You just get only cycles. Okay. I understand what you mean. You just get the product will be cycles of length k. Yeah. Okay. Then you want to get rid of the other elements by a combinatorial trick. But there is some problem. Yes. I don't think it's so simple. Yeah. There is some problem. With the here. Yes, it should be k here and k minus 1. You're right. Thank you. Yeah?
So you divide the Jn by n and then you raise to the power k minus 1, right?
Yes, this is okay. Yeah. Okay, so you see this is a kind of Jn over n is this. So it's a kind of law of large numbers for the transpositions in some sense. You want a law of large numbers. It's not really a law of large numbers because the limit is it's not a number but a probability measure. But it's okay. So the idea is you have a law of large number here. Okay. So now there is the issue. So what we have seen is that all the Thoma characters can be obtained from irreducible characters by taking limits. Okay. Then there is the issue of why are they extremal and things like that. Okay. So this is what I will explain next time, because I think in 5 minutes I don't have time to go into this. But what you will see in the next lecture, if you come, so it's that essentially the same tools as what we use here. So very crude estimates on permutations. So you see, essentially what we are using on permutations here will be essentially the size of the permutation measured by the number of points which are not fixed. That's all. It's a very crude estimate on the size of a permutation. Okay? And this is the only thing we know in order to do all these asymptotics, the law of large numbers. Okay? But then, of course, there is the other. Now, there will be the problem of what happens when my diagram, instead of growing like n, like that, remains a very compact diagram where, for example, you would have a diagram whose size here would be of order square root of n. Okay? You can have, for example, you can have a square. Then I will make, in this case, I will make a scaling by square root of n of the diagram. And I will make a scaling by square root of n of Jn. The Jn will go to 0. We will be in the case where the limit measure will be 0. The Dirac mass at 0. So we have to do another scaling in order to see something. Okay? So I will make this other scaling. And then we will use a computation like that, but then we will have to be much more careful in the computation. And instead of using this very crude analysis of the permutation by counting how many points are non-fixed, we will have to count the length of the permutation in the Cayley graphs that I introduced in one of the lectures. Okay, we'll have to do that. And so there will be some connection with maps, genus zero maps. Because genus zero maps are given by factorization in the symmetric group. So what we will do, we will make a fine analysis of this factorization in the symmetric group, these genus zero factorizations. And we will make an analysis, an asymptotic analysis of this diagram. And then what we will see is that the crucial tool for understanding this case. So in this case, we see we saw today, and we will see next time, that the representation theory of S infinity is what you need to understand the asymptotic in this scaling by n. And in the scaling by square root of n, we will need a completely different theory, which is free probability, which will explain what happens to the characters, what happens when you perform operations on the representation, like taking induction of representation, restriction, and things like that. Okay. So this I will explain also for the case of infinity, but in some sense it is much simpler. It's like a bit like the law of large numbers compared to the looking at the fluctuations. Okay. So in general, law of large numbers is simpler, and then when you go to the fluctuation, you have to go at the next. Okay. And in the end, we will come back to combinatorics because we will see that we will get some asymptotic formula for the characters and using some new parameters. And we will see that using these new parameters, we will be able to write actually exact formulas by making expansion a little longer. And these exact formula carry a lot of combinatorial interest for symmetric groups. So certainly, I don't know. So Valentin is a great specialist of this last part. But I don't know if there have been any exploitation of these things for maps. Actually, you know, je sais pas si toi tu sais si les cumulants libres ça sert pour les formules que ça donnait pour les cumulants libres, pour les caractères intérieurs du cumulant libre, et ça sert pour les maps, on ne sait pas. Ça devrait. It should, because it's you are going beyond genus 0 is the first, you get some free cumulants, and then you go beyond genus 0, and you look at the expansion. You have quantities which will be defined in terms of some genus 0 expansion, and then you will need to, but then you will get from these quantities exact formulas. So, and we know the exact formulas, they should involve all the genus. So there should be some connection, but I don't know. Okay, so anyhow, we will see that next time. And okay, so thank you.